Limit Laws, Part 6. Let's look at some more indeterminate forms that will require us to do more work in order to evaluate the limit. The strategies we'll see in this video are expanding, combining rational expressions, and some more graphing the function. We need to evaluate the limit as h approaches 0 of the quantity 3 plus h to the negative second power minus 3 to the negative second power all over h. Now, these negative exponents are not helping us here. Sometimes they're useful, like if you're simplifying some sort of expression where you have a lot of exponents, but they're not helping here. So let's rewrite these by finding the reciprocal. So we have the limit as h approaches 0 of, well, that 3 plus h to the negative second power will be 1 over 3 plus h, and that negative, well, that 3 to the negative second power will be a 1 over 3 squared, which is 1/9. And this will all be over h. And now it'll be a little bit easier to substitute into this. So this is equal to, whoop, forgot my squared here. There we go. Thought something was strange. So this is equal to 1 over 3 plus 0 squared, which gives us 1/9, minus 1/9 over 0. So we have 0 over 0, which is indeterminate. And we must do more work. So we could either multiply by the least common multiple, or we could combine rational expressions. I'm going to do this by combining rational expressions. I'm also going to rewrite this so that I can save some space. So I'm going to rewrite this so I have the limit as h approaches 0, and instead of doing this all over h thing, dividing something by h is the same as multiplying something by 1 over h. And that will just save me a little bit of space. So I have the limit as h approaches 0 of 1 over h times 1 over the quantity of 3 plus h squared. Sorry that I forgot the squared the one time. Minus 1 over 9. And I want to combine these rational expressions here. And in order to do that, I need to figure out what is missing. So there's actually no common factors between these denominators. So that means that I need to multiply this expression by 9 over 9, and this expression by the quantity of 3 plus h squared over the quantity of 3 plus h squared. So this is equal to the limit as h approaches 0 of 1 over h times 1 over the quantity of 3 plus h squared times 9 over 9, since that's my missing factor for that fraction, minus 1 over 9 times the quantity of 3 plus h squared over the quantity of 3 plus h squared, because that's the factor that is missing from that rational expression. So let's see, now we have the limit as h approaches 0 of, let's not forget our 1 over h, times, well, 1 times 9 is 9, and 1 times the quantity of 3 plus h squared is that 3 plus h squared. And this will be all over that common denominator of 9 times the quantity of 3 plus h squared. And now I look at this and I go, oh man, I still end up with a 9 minus 9 if I tried to use direct substitution now. So I still need to do something about this numerator. And before I can do anything with that numerator, I'll have to expand it. So I have the limit as h approaches 0 of 1 over h times 9 minus, well, 3 plus h squared is going to give me 9 plus 6h plus h squared and I still have that 9 times the quantity of 3 plus h squared in my denominator. Okay, now I can see that when I distribute this negative, I'm going to end up with a 9 minus 9. So I have the limit as h approaches 0 of 1 over h. And then I also notice that what's left, both have these h's here. So I'm going to also factor out an h. So I have h times negative 6 plus h. Oh, minus h. I thought and I still did the wrong thing. All over 9 times the quantity of 3 plus h squared. And now I can see that this 1 over h and this h here have a common factor of h, so they will divide out. And that leaves me with the limit as h approaches 0 of, well, 1 over 1 is just 1, so that first rational expression is gone, and I'm left with negative 6 minus h over 9 times 3 plus h squared. And it looks like now when I use direct substitution, I won't have a 0 over 0 anymore, so let's try that out. So I have negative 6 minus 0 over 9 times 3 plus 0 squared. And when I look at this, I go, oh man, I do not want to do 9 times 3 squared and then have to worry about that 6. So I'm just going to look for some common factors now. There's many different ways we can do this, but the first thing that jumps out to me is that I have a common factor. This 6 is 2 times 3, and this 3 squared is a 3 times 3. So I can divide out one of my 3's, and I'll be left with a 2 in my numerator and a 9 times 3 in my denominator, which means that I have negative 2 over 9 times 3, which is 27, and that is what my function is approaching as h approaches 0. We need to evaluate the limit as x approaches 5 of 5 minus x, all over the absolute value of 5 minus x. And I can already tell that something strange is going on here. But let's try direct substitution first. So we have 5 minus 5, all over the absolute value of 5 minus 5, which will give us 0 over 0. And this is indeterminate, not indeterminate. So we need to do some more work. Now, we could try to split this absolute value function into 2 pieces and treat it like a piecewise function and try to simplify the different pieces and figure out what's going as the domain of each piece switches. But that's going to be a lot of work, so it might be a little easier to try to graph this function instead. And there isn't really a set way to try to graph this. So let's just try some test points on either side of this 5 that's giving us some trouble. So let's find f of 3, f of 4, can't find f of 5, but we can find f of 6 and f of 7 hopefully. So f of 3 will give us 5 minus 3 over the absolute value of 5 minus 3. So that'll give us 2 over the absolute value of 2, which is equal to 1. F of 4 will give us 5 minus 4, which is 1, over the absolute value of 5 minus 4, which is the absolute value of 1. So this will simplify to 1. Okay, now let's look at f of 6. So 5 minus 6 will give us negative 1, and then this will be over the absolute value of 5 minus 6, so the absolute value of negative 1. So we have negative 1 divided by 1, which is negative 1. F of 7 will give us 5 minus 7, which is negative 2, over the absolute value of negative 2. So that's negative 2 divided by negative 2, which is negative 1. And this type of pattern would continue. When we have a number that's less than 5, we'll divide out to a positive 1. When we have an input that's greater than 5, we'll divide out to an input that is, we'll divide out to an output that is negative 1. So we've kind of figured out what our two pieces are going to look like, and now we can sketch a quick graph. Okay, so 1, 2, 3, 4, 5, 6, 7, 1 and negative 1. We know that, well, let's see, I'm going to treat these guys as purple. So we know that f of 3 is 1, and we know that f of 4 is 1. And I suspect that anything less than this would also be 1. So we're going to end up with this sort of horizontal line where we're just not really sure what's going on at 5. There's some sort of discontinuity there, and we have to figure it out. And let's also take a look at what's going on the right side of 5. So f of 6 is negative 1, and f of 7 is also negative 1. And really anything that has an input greater than 5 is going to have an output of negative 1. So we end up with a graph that looks something like this. And we can see that the left and right limits are not equal. So the overall limit does not exist.